All right, back to themes.
Hello.
Hello. Today is what is the theme? Just hat?
Hat day? Silly
Crazy hat day?
Yeah.
Are the things that we're wearing, are they counted as hats? I feel like for both of us it's a helmet.
I don't think this is a helmet. There's no
Mary Kate's gonna take a is gonna appear in the video. Say something.
Hello. Roar.
Roar. All right, it's Crazy Hat Day. That's the end of that. Let's proceed. Go ahead and share my screen. Today, we are still in Unit 7, and we'll learn why we're still in Unit 7, this triangle unit, in a second. But we're going to begin our journey on the study of vectors. Triangles do play a big role in this. With that said, there's two ways to look at vectors. Geometrically, like visually, and then also we can describe vectors with numbers. And we'll get into that in a second. So on the screen, we have two vectors, A and B. Mrs. Contreras, what do you know about vectors?
Boom. They have a magnitude and a direction. So they have how long it is and where it's going. So it's different from a scalar, which is just a number with no direction associated with it.
What are some things that are vector quantities? What are some things that both have a direction and a magnitude?
Velocity, right? Because if you're going straight, like if you're going forward, that can be like a positive velocity, but if you change direction, you go backwards, that's a negative velocity.
Yeah, so if you have a two-dimensional number line, like moving that way a certain speed. Yeah, I got you. What else is a vector quantity?
Mosquitoes. Mosquitoes are vectors.
Mosquitoes are vectors. Why are they vectors? I've actually wondered that. Help me conceptualize why we call mosquitoes and like people that might be infected with some sort of disease. Why do we call those vectors?
Because the direction of the mosquito biting matters. So if mosquito bites something that has malaria and then bites something else that doesn't have malaria, then malaria gets transmitted. But if the order changes where the mosquito bites something without malaria and then bites something with malaria, then malaria doesn't get transmitted. Not malaria doesn't get transmitted either.
I never understood why we called it vectors, and now I do, and I'm really glad. I learned something today. Awesome.
Nice.
Sweet. So there you go. I had some more in my brain, but I forgot what they were. Force. Force is a vector, right? Because you're applying an amount of force, but also in a specific direction. Work, I believe, is a vector quantity. No, work might be a scalar quantity.
Because you're integrating, right? Yeah.
Yeah. So we got everyone at home. Think about some things that that have both a direction and a magnitude. That is what a vector is. And these two pictures here.
The reason force is a vector is because force is mass, which is a scalar, times acceleration, which is a vector.
Oh, acceleration is another vector quantity. Oh, yeah, because a scalar times a vector is a vector. These are all things that we're going to get to. Oh, I like this. All right, so we have two pictures here, A and B. How does an arrow describe these two values, a direction and a magnitude?
Because the arrow is showing where it's going, and how long the arrow is the magnitude.
Oh, so like literally the length. So B has a smaller magnitude. They're pointing in different directions, but the length of B is describing its magnitude.
And it's smaller than the length of A, which is the magnitude of A.
So we need to write to Kami, because I don't think there is a measurement tool in Kami's interface. So we're not going to actually determine what the magnitude is. But A is looking to about twice as much as B. I don't know, maybe a little bit less than twice. We're going to skip the magnitude in this video, but if you have a ruler at home, literally measure. And in terms of geometric vectors, the length is the magnitude. Because here's another vector that has the same direction, but a different magnitude, called like A prime or something like that. So the length of that vector is going to describe its magnitude. Geometric vectors are really good, though, for describing what it means to add vectors. So we're going to do that here. We have the vectors A repeated twice for A and B. But what we want to do is we want to add vector B to vector A. That's this one right here. How do we add vectors. What would be a reasonable way to add pictures?
We need to combine their directions and their magnitudes in
Mhm.
some kind of way. And so we need to take that into account. So like if you're thinking about if you were like a particle or an ant traveling, or a dinosaur or an astronaut traveling along vector A, and then you travel along vector B, then you should have the end of vector B match up with where, or the beginning of vector B match up with where vector A ended.
It's almost like a journey. I'm going to go ahead and copy vector B here, do a little bit of commie magic.
Oh, you're not using the line tool?
I guess I could have. I probably should have. I'll do that for the next one.
Don't stop believing.
Okay, so we have A. Here's B. So it's kind of like a journey, right? Like the astronaut. No pun intended. I love that. The astronaut's going on a journey A and then goes on a journey B. So that's kind of like the net direction. You started here. You ended here. Let me go ahead and change the color. Let's do orange. Oh, and I feel like this is also giving us the magnitude as well, because we now have a new arrow that has its own length.
What
Wait,
should we
so-
call that? Is there like
I feel like you just call it A plus B.
A plus B, which is still a vector though, which is helpful.
That's true. Vector plus vector is going to be a vector. Notice these little hats I'm giving them. Let's zoom in super close on A
That's
plus
why
B.
we're wearing hats, Mr. Kirk. It's
Oh,
because
is that why you do
these are
that?
vectors. No, I just really like hats.
Okay. So if you look, it's kind of like a half arrow right there. That's what we put on top of variables to signify that they are not just a number, a scalar, but also they are a vector. They also have that direction, not just the magnitude. Let me go ahead and zoom back up.
That's like a handwriting kind of notation. If you have access to a computer, then typically we write it in boldface.
Yeah. So you'll see these two different things bold. There's actually some other symbols like specific vectors that we'll get to later have a different symbol above it, a little hat, a little caret on top. That signifies something else, specifically something called a unit vector, a vector with length 1. We'll get to that later. There you go, A plus B. Look at the magnitude of A, look at the magnitude of B, and then look at the magnitude of A plus B. What's weird about it?
It's smaller.
It's smaller.
But it makes sense because the directions are totally different.
It's almost like B has a negative value.
Yeah. Well, at least in like the vertical direction, but B has like a positive value in the horizontal direction because A plus B is further to the right than just A by itself or B by itself.
Yeah. Magnitude's always going to be positive, and the direction is going to kind of tell you, like, it's almost like back in the day when you did numbers. Like if you have 0 and you have 2 and you have -2, their magnitudes are the same. They're both 2 units away from 0, but that negative is kind of describing a direction. We don't go ahead and call them vectors, but the direction of a vector is kind of describing whether it's positive or negative in terms of a reference frame, a frame of reference. All right, so A minus 2B, what do you think is going to happen there? Minus 2B.
Well, we've talked about this before, where addition and subtraction are actually the same thing, right? So maybe we can think about it in that way, where we have A plus -2 times B.
A plus -2 times B. Okay, so what does it mean to multiply a vector by -2? Maybe we can think about this picture I just drew. Like, what does it mean to multiply a magnitude by -1?
That you would flip the direction. So it goes in completely the opposite direction that it was going before. But when you're drawing it, you could just draw it as the same magnitude, but then put the arrow in the other direction.
Yeah, let's do that. All right, let's go back to blue. Let me do the line tool just to be fancy. Yes. Fancy. Ooh, we get like a nice.
Look at that. Oh, you get an angle too. Then we could fill in that direction part.
We could. Let's not worry about it.
Students could.
We can think of we can use something that we've been studying for the past 2 months to figure out directions when it comes to these things.
Math.
Oh no, my little arrow didn't come, and we'll leave it. So that's 1 negative b. And let's see if I can do a
Exactly.
little copy paste magic. Nope.
Oh, so sad.
Boom. Bam. Bam. Pow.
Nice.
Boom. That is a plus 2 negative b's.
Nice.
Boom. All right. So a plus 2 negative b is going to be from the beginning, the journey the astronaut went on. And I'm going to use the straight line tool.
Yeah, I'm
But I
about to
want
drop
orange.
a straight line. There you go.
You're about to drop it? Thank
Yeah.
you. Oh, but it's not
I was
orange.
like, oh no, he's doing it by hand. Oh, you want it to be orange?
Yeah,
Yeah.
totally. Or like orange is the color of vector sums. I've decided.
That's not a thing.
So that is a. I'm gonna go ahead and write minus 2b. Boom. All right. In this case, it looks like a minus 2b minus 2b ended up being bigger than a and b combined. So that's kind of interesting. Negative b, negative b. Boom. And so big idea on this page is adding and subtracting vectors. You are head to tail is what we sometimes say. The head of one vector is attached to the tail of the second vector. And then we can flip-flop vectors. Negative just means in the opposite direction, just like kind of that on the number line. Cool. We have magnitudes, we have directions, but we'll get to those when we get to algebraic vectors. Let's go ahead and segue to that.
We should put up a picture of a segue.
I was literally drawing one. All right, algebraic vectors.
So you got to graph the vector with an initial point and a terminal point. So does that mean that we have a starting and an ending point?
Yeah, so let's go ahead and do that. -2, 5, boom. 4, 4. And then if I connect them, we're kind of back in page 1 land, where we have like a geometric vector going on. Boom. Bop, bam. Right. Write the ordered pair. So a vector going from -2, 5, and 4, 4. Write the ordered pair standard position vector that represents this vector, then find its magnitude and direction. So before we do any of that, look at this vector that we have.
Yep.
Can you describe its magnitude now that we're in the coordinate plane without a ruler?
So we have what? A vertical change of 1 and a horizontal change of 6. So then that's going to give us, oh, and then if we square root that, that's going to give us the distance between our 2 points, aka Pythagorean theorem. So what is that? 37?
Yeah, root 37.
37
yeah,
is going to be the magnitude.
So root 37 units. I'm going to go ahead and add next to yours the notation we usually use for magnitude. There's 2. Sometimes people just use, let's call this vector AB, by the way. We're going to use 2 letters here, just because that's what we were given. Sometimes people put the absolute value bars, because absolute value represents magnitude in normal numbers in that 2-dimensional line, a 1-dimensional line. But sometimes you'll see double bars. So I want to just introduce that. Sometimes you'll see double bars for magnitude for vectors. But there you go, root 37. Root 37 units is how long that arrow is. What's its direction? How can we describe its direction?
Well, I'm thinking, like, what's the slope of this line? Or what's like the slope of the line that goes through where this vector is, which is, I think, what, -1.
Rise over run, -1/6. So the slope of this thing is -1/6. Okay. Is that what you want to describe the direction as?
No, because I think that we should also deal with this using what we've been using before of like angles. I think that would help. So we could think of this as,
I just had a brain blast.
Mm-hmm.
And I don't know if I've ever thought about it this way. What did I say 1,000 billion bajillion times slope is when we were doing trigonometry?
Tangent.
Is the angle of this with respect to the x-axis not just the tangent of the slope?
Mm-hmm.
What's that going to give us? -1/6. Let's see if I can Grab my calculator real quick. Got my simultaneous bag here. There's a blue calculator in it. Boom.
Ooh.
The tangent of -1/6 should give us the slope that is making, as long as I am in the correct mode. -1 divided by 6. I'm getting a wrong answer. I know why I'm getting the wrong answer. What am I doing wrong?
Are you in degrees or radians?
I'm in degree mode, but this is a ratio. What is tangent supposed to evaluate? What are all the trig values evaluating?
Oh, on a unit circle, what's happening?
Yeah, we're evaluating angles. -1/6 isn't an angle. It's the output. I think I need to do arctan.
Arctan.
Arctan
Because
of
tangent
-1/6.
of theta equals -1/6, so then -1/6 equals.
This is going to be our angle theta. The angle theta being this thing right here, and that is -6. Boom, boom, boom. -9.46 degrees, which totally sounds kind of right.
Nice.
I'm going to go to 3 decimal places too. All right, exact answer, approximate answer, and you just moved it down to the origin. I like that. Why did you do that?
Because I read the question while you were using your calculator, teamwork, and it said, write the ordered pair standard position vector that represents this vector. So standard position vector means that you're starting at the origin, and then you're going in the proper magnitude and direction, which is that.
Your green vector and my blue vector, they have the same magnitude and direction, right? -9.462 degrees with respect to, I guess, east, or the positive x-axis. They're both √37. So they are the same vector. Vectors don't have location. The two values that they represent is magnitude and direction. So they can be wherever you want. So if we relocate it to the origin, how can we describe that vector way more efficiently than -2, 5 to 4, 4?
Well, we can use Wrangle and Langle, our like square pointy notation, and then just have the coordinates of the end point. So what's that? 6, -1. Oh,
you got it. You got it. I'll let you do it.
That's cool.
You got it?
Cool.
Did you see my A-B there?
I did.
Cool, cool, cool. Cool, cool, cool.
And boom. Oh, boom.
Sweet.
So we have 6 in our x direction and -1 in our y direction for our terminal point of our standard position vector. I never knew it was called standard position vector, but that's fun.
And like the 6 and the -1 are kind of appearing up here. -1 squared. We wrote 1 squared because we were looking at magnitudes earlier. But if we think about the height being -1, then it's appearing up there too. We tend to, when dealing with algebraic vectors, we don't put the vector just anywhere. We always try to center it at the origin so that we can describe it with just one coordinate pair rather than 2 coordinate pairs. And some really cool algebraic formulas appear if we decide to coordinatize, that's a really hard word to say, our vectors around the origin. So there you go, we have a vector. Let's look at adding vectors. Add the position vectors below, find the magnitude and direction of the resulting vector. We're not doing this geometrically. We're not going to, well, we will draw it because we have a graph, but the goal is to describe u plus v with a coordinate pair rather than pictures.
Can we just add up the values, the corresponding values?
I think so. Let's make sure that that is true. So we have 3, 2, 1, 2, 3, 1, 2. That is this vector. We have the vector -6, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. We have these 2 vectors, and we want to add them. How do we add vectors again?
You said you got to go what, tip to tail or something?
I'm going to reposition. Why don't you move that blue vector you just drew over? Yep, awesome. And then if we position
I
it
know, I did that right.
perfectly, I think you need to go like over a tiny, to the right a tiny bit and up a tiny bit with your blue vector. I think we want to end
So difficult.
there.
So tiny.
I
I'm zooming in. Ah,
I put a little dot at the terminal point for our two vector sums.
cool.
Boom. Right? The resulting vector, which I will still use orange for, is that thing. That is u plus v. Do we get what you claim to be the sum of vectors? Just the sum of the components.
Yeah, because this is what, -3, and that's 1, 2, 3, 4, 5, and 6.
So 3 plus -6. So u plus v. Let's see if this is true. 3 plus -6, comma 2 plus 4. That is -3, comma 6. And that is the orange vector, -3, 6.
I think so.
Sweet. So slowly but surely, we're going to kind of, I'm going to call this graph training wheels. We're going to remove the training wheels. We can do almost all of the vector math that we are going to need to do algebraically. If we want to add two vectors, instead of drawing the pictures, let's just add the components. The first vector tells us to move 3 to the right. The second vector tells us to move 6 to the left. The first vector tells us to move up 2. The second one tells us to move up 4. So we can decompose vectors into their components. We need to find the magnitude in the direction of the resulting vector. I feel like that's just going to be the Pythagorean theorem, right?
Mm-hmm. And then arctan?
But it's more specifically, arctan, more specifically, instead of finding the length of the green one and the length of the blue one, I think we can just do.
Oh, trig.
Yeah.
Yeah. Because we have 1/2. Wait. Yeah.
So arc,
And then root 0.
tan. Oh, wait, no, we have an issue. Arctan of 6 over -3. Rise over run. Arctan of -2. What is the arctan of -2? Arctan of -2 is -63 degrees. -63.435. How do you feel about that angle? Is that the angle?
Like it's not correct. I feel like we need to do like 180 minus that.
Yeah.
Or 180 plus that, I guess.
180 plus that, right? Yeah. Well, so currently we have this vector. And we need to add 180 to it. So 180 plus whatever we were given. So we do need to be careful. Arctan does have a domain restriction, or sorry, a range restriction. But we need to add 180. Theta equals, in this case, 180 plus that. Which is plus 180, 116.565. That's my Star Trek voice. 116.
Nice. You had an equal sign that was no longer valid, so I just made it not equal sign.
Thank you.
It was bothering me.
As it should, as it should. All right, so let's add, subtract, combine algebraic vectors. We've kind of done it already. 3, 2, and -6, 4. We established that it's really just adding, so let's do a little bit more complicated ones, hardly, and call it a day on that.
Cool.
2m plus n. 2m, that's 4 and -3. Did we decide that 2m we just multiply through?
Yeah.
Yeah.
Right. We have to distribute, right? Like it's like pretty much what's happening, that you're scaling up the x direction and the y direction.
So it's like 4
or the horizontal and the vertical.
It's going to be 8 -6. So we have 8 -6 plus n. which is 3, 0. Will be 11, -6. This is as easy as it looks. It is just adding and subtracting like we've done since I don't know what grade.
Earlier than this.
Yeah, earlier than this. But coordinate wise, right? X's go with X's, Y's goes with Y's. Eventually we're gonna add a Z. And the Z's will go Z. Right? M minus -2, minus positive 2n plus P. 4 minus 6 plus -1. Is that -3?
Yes.
And
I wasn't really listening, sorry.
Hopefully it is. -3, 0, 2 times 0, and 5. That's 2. Right? We're just adding and subtracting coordinate wise. Right? This one's going to look like it's going to be 4 negative. And never mind. I don't feel like drawing it. That sounds like a lot of extra work. All right, let's keep going.
Cool.
All right. The concept of a unit vector. So any vector can be expressed as the resultant of a horizontal and a vertical vector. A vector that has magnitude 1 is called a unit vector. So just scrolling back.
Just like unit circle has a radius of 1.
Yeah. So any vector extending from the origin to the unit circle, we're going to describe as a unit vector.
Wow.
Cosine and sine might play a role there.
Wow.
Let's see. We had a magnitude a while ago, root 37. That is not a unit vector. That's root
Nope.
37 bigger than a unit vector.
But if we divide that vector by root 37, like multiply it by 1 over root 37, then would we make it into a unit vector?
Yeah, we're scaling. So we have a triangle, 6, -1, root 37. If we divide this by root 37, we divide this by root 37, and we divide this by root 37, we are on the unit circle. Nice connection to the unit circle. I don't usually think about it that way. But if we
It's just like a
divide
unit.
by the magnitude, we get a unit.
Yeah.
Sweet. Right, let me scroll down. Before we get into just generic unit vectors, we do have some unit vectors that are kind of commonplace, and we give them special names. So we have the unit vector in the direction of the, you got me. That was like a boom.
Mhm.
We have a unit vector in the direction of the x-axis. We call that I. And if my I's and J's are ever similar, let me know. I take pride in, one year I was like, I'm going to do I's and J's so different. It's going to be great. There's my I. Basically, I just do a little swirl in the other direction for J. Yep. And J, length 1. They're pretty similar.
But you're like very responsible and you like put the little dot. Like a lot of times I just do that.
Waiting for it.
I just replace the dot.
I mean, like it's like the arrow is the dot. No, I'm fine with that. That's totally cool.
It is responsible to put it there. So I put it in. So it's subtle.
But it says any vector can be expressed as the resultant of horizontal vectors and vertical vectors. So like if I give me a vector that can be placed in this coordinate plane that we have here.
Should I just draw it in?
Yeah, just draw it in. And then I'm going to find out how many I's and how many J's get me to that vector. All right. Ooh, making me go in the other direction. So -2 I's. Let me go ahead and with Kermit the Frog green. -2 I's. And really, when I write I, I'm in a way writing 1, 0. And then it looks like -3 J's.
And if you're really excited about vectors, then you can look up what basis is. Basis.
You're stealing words out of my mouth. That was my next. That was my next comment. I and J form a basis for the 2D plane. You can construct any vector in the 2D plane using I's and J's, and that's kind of the essence of what Mrs. Contreras is getting at here, being a basis for a space. If we had in 3D, we're going to have 3D vectors. 3 vectors can form a basis for that space. as long as you can get to any vector with those 3 vectors. Real quick, let's just why not? Just bouncing off of that. Let's say I have this vector and this vector. Do they form a basis for the 2D plane? Can you get to any vector with those 2 vectors?
I think so, because what you have is 2 vectors that are not necessarily lining up, where they're scalars of one another. And so from that, you can get to every location in our coordinate plane in R2, because those 2 vectors that you drew, the purple ones, are not there's a geometry word. What is it, collinear or something?
Parallel?
Parallel. They're not parallel?
Yeah. They're not parallel. So I just arbitrarily, while you were talking, put a point on the plane, and I'm like, how many of the one vector and how many of the other vector get me there? And I don't know what the actual decimal is.
But smaller than 1.
So some amount of this one is right here. And then some amount of the other one is right here. And then those in combination can get me to any point. You can pick any point.
I really like that you used combination, Mr. Kirk, because it's a linear combination. You're taking a scaled version of each of those vectors and adding them together, but you're not squaring anything or cubing anything. You're just taking those 2 lines and adding them up with some scale. So it's called a linear combination. And those are linearly independent vectors.
I love all this vocabulary. All this vocabulary might be going over your head, everyone, but that is okay if you're interested in vectors as much as we are. There's a course at Blair that you can take.
It's called linear algebra.
It's called linear algebra. Do you do algebra with linear objects in linear algebra? Never mind.
Yes.
All right. So write AB as the sum of unit vectors for A and B being those 2 things. This was obviously kind of formatted poorly. That should be right there. Let's leave this one for a question in the video. Boom. We have A to B that is some vector. How many i's and how many j's represent that vector? Right. This is a harder question, but we've actually already kind of answered it. Awesome. Find a unit vector, a vector of length 1 in the direction of 6, 4.
So what is the magnitude of our vector 6, 4?
So let's see, 6, 4 is I like to draw pictures. Never hurts. The magnitude, I'm going to Pythagorean theorem it up. 6, 4, 36 plus 16 plus 36 is 52.
I did 24 in my head as well. That's in my brain. Yeah. Okay.
You did 4 square was 24 also. 6 times 4 is 24. So it's kind of, all right. So we got square root of 50. All right. And we want a vector in the same direction as this, but only 1 unit long.
Can we just divide by root 52?
Yeah, we mentioned this earlier. Divide by root 52. And then that will give us a vector. Here's the unit circle. That'll give us this vector right here. Right. 6, 4 divided by root 52. What would the with all of this algebra done in general? What is the formula for a unit vector given a vector?
Given a vector, let's call it u.
When I said i's and j's earlier, I definitely meant my u's and v's. One year I wrote on the board 100 u's and 100 v's to make them different.
That's a lot.
I's and j's I haven't done yet.
Okay.
I just misremembered.
Oh, you do v like that. See, I give v a little
You do whoop.
Yep, on the right.
Yeah. Oh, see, I see what you're doing, but I like to, if I don't put a little swirl, then my u's totally look different. Hey, can you tell me why math people like to use u's and v's in the same problem always?
Nope.
No. Anyways, okay, so we have u, and let's go ahead and say that it is a comma b. I guess maybe x, y might be better, whatever. What is the unit vector? Oh, and I mentioned this at the beginning of the video. We actually give a special symbol for unit vectors, a caret hat. And I say u hat. Like I literally say, when I'm talking about a unit vector, I say U hat verbally.
Mm.
What is the unit vector given A, comma, B?
It's going to be A over the magnitude of U, comma, B over the magnitude of U.
And then the magnitude of U is the square root of A squared plus B squared?
Mhm.
Sweet.
This is way more writing than I thought we were going to do. I thought we were going to do that U hat was U over magnitude of U, like that.
Oh, so fine. Oh, you got it. And you wrote it right where I was going to write it. Boom. U hat is U divided by the magnitude of U. Awesome. Yeah. That's probably the most important formula of all the things that we wrote here. That's actually saying what we mean. Everything else is just a bunch of symbol jargon. Okay. Let's proceed. We're knocking out a lot of the basics of vectors today, everyone. All right. We already talked about parallel vectors a little bit. Right. Graph the vector with initial point 3, -2 and terminal point 7, 4. How about you do that and I'll graph the second one. -4, -2, -2, 1. -4.
7 is such a big number.
7 is?
Yep.
-2, 1. Terminal point. Yeah. C, D. Nice. All right, I am going to grab mine and I'm going to reposition it onto the origin so I can identify what my coordinate pair is.
Okay. Oh, you're just moving it.
Heck yeah. You do yours. You do yours too. So mine is 2, -3. There's many ways we could have gotten to -3. We could have just done simple adding or subtracting.
Mm-hmm.
Oh, I like that you changed the color. Thanks.
Yeah.
Oh, you're better than me. You copied it.
No, I changed the color. Like I drew over it and then I changed the color. But it was just because it was too hard to see. And we also had very subtly different blues.
It's true. Well, it's almost like a good thing that it was going to be blue and like a subtly different blue, because what do you notice about the vectors now that they've been coordinatized?
They're in the same direction, but they have different magnitudes.
Okay. I feel like I can get to your vector by multiplying my vector by 2.
That's true.
What's yours? 4, 6. Mine's 2, 3. 4, 6, 2, 3. What is like a sentence we could say about vectors that are parallel?
They are scalars of scalar multiples of each other.
Vectors that are parallel. Vectors that are parallel are scalar multiples of each other. And I think, we have something we can write. But if I stroll down, yours is 4, 6, mine was 2, 3. When are two vectors parallel? I think we could. Direction. Yeah, same direction. I'm going to go ahead and say 2 vectors, U and V, are parallel. Oh, let's get fancy. If and only if U is equal to K times V for K contained in the reals. Notice there's no hat on the K. There's no arrow on the K. It is a scalar.
K is scalar.
It's a real one. Here you go. When are 2 vectors parallel? When that is the case. Our scalar multiple here is for me 2, for you 1/2, right?
Yep.
Cool. All right, let's keep going. We got one last thing to do here. Perpendicular vectors. Graph the vector with initial point 3, 2 and 7, 4. Is that the same for you?
No.
Oh, that 3, -2 is now 3, 2. All right, you get that one. I'll get the other one. I'll get C and T again.
I'm hoping that it's also. Yeah, because you used to have these grids as like 10, -10 to 10, but now they're 8 to 8, negative 8 to 8.
So I threw you off.
It threw me off. Okay. I'm just complaining.
And that's allowed. I wanted magenta. What the heck? That's what I'm complaining about. And then there's my coordinate D. Boom. All right, let's do some little magic. Let's shuffle these on over. We intentionally use different colors this time, so we are in business.
Yeah, totally on purpose.
I got negative 1, 2, 3, 1, 2, 3, 4, 5, 6. I got negative 3, 6.
Mine's not being nice.
Is something not coming with it? Is
Yeah,
A
it's
and
not
B?
coming all together.
Oh, is the majority of it coming?
No, I'm just messing stuff up now. Oh my gosh, what a disaster. Okay.
You're like doing it like
This
things
is
that,
not working.
that's annoying. Hey, there it is. 1, 2,
Wow, so painful.
4, comma 2. 4, comma 2.
Hmm.
All right, are our vectors perpendicular? How do we test perpendicular? How do we test if something is perpendicular with something else?
Negative reciprocal slopes.
Yeah, let's look at the slopes. All right, my slope is rise 6. No, negative 6, run 3. My slope, I'm going to say M subscript M for magenta.
So
Negative 6 over 3. Mine's negative 2. Yours would be M sub G. Yeah.
it's positive 1/2.
Positive 1/2. Negative reciprocals, right?
Yes.
Boom. All right. So with that said, when are two vectors, that should say perpendicular.
Perpendicular. We should have done
Per.
this in pirate voice.
I was gonna say you did a pirate voice there, didn't you? When are two vectors perpendicular? All right.
When they're not scalar multiples of each other, but that's not exact enough, right?
Well, so let's inspect our vectors. All right, your slope is 1/2.
Mhm,
My slope was negative 6 over 3.
mhm, mhm.
Or I could even say like 6 over negative 3. What is the slope of our vectors given a vector? If I give you any vector, what is its slope?
Its slope is its when it's like lined up at its initial point.
Well, so if I were to give you 4, 2,
Mhm.
what would be like a speedy way to just know the slope?
Take the second over the first coordinate.
Second over the first, right? And the second is the rise and the first is the run. Let me scroll down. Let's give ourselves two vectors. So vector U, A, B. Vector V. Let me not forget these. What are you feeling? CD?
CD.
CD. Remember CDs?
Yeah.
Anyways, what is the slope of the vector U?
B over A.
B over A. What is the slope of vector V?
D over C.
D over C, okay. And what is true about these two slopes? Can you give me an equation?
That B over A must equal negative C over D in order for those two vectors to be perpendicular.
Right? Because negative C over D, negative reciprocal, would be negative C over D. So these two things must be equal. Okay, what are you feeling with this? B over D is equal to negative C over D. B over A is equal to negative C over D. Can we like move things around?
Yeah, can we multiply by like D over C to get like dB over CA equals -1?
Well, being a geometry teacher myself, when I see two fractions equal to each other, I think of like something that some teachers hate, but I don't like that teachers hate it. Do you know what I'm talking about?
Like flip, cross multiply.
people don't like cross multiply. They're like, oh, like multiply by the denominator on both sides, like multiply by AD and AD. I cross multiply. BD negative CA. Let's go with negative AC for alphabet reasons.
Mm-hmm.
I'm going to add AC to both sides. What do you think about that?
That looks true. It's interesting because it looks like we took our first coordinates and multiplied them together, and then we added them to our second coordinates, multiplied together, and then we get out 0. I wonder if that's something.
So for any given two vectors, if we multiply their x's and we multiply their y's and we add those two new numbers, if that is 0, the vectors are perpendicular. It's like a way of multiplying two vectors. This whole time we took scalars, we can multiply vectors, we could add vectors, we could subtract vectors. We never talked about multiplying vectors.
But it's
so
like component wise.
Right? It's
like
not
the first and the first are getting multiplied, and the second are getting multiplied. But it's not like crossing, I don't know, like
like if I gave you two, like if I gave you 1, 2 and I don't know, 7, negative 4.
Mm-hmm.
If I said multiply those, I don't really know what that would mean.
Mm-hmm.
But like this is kind of like multiplying them. Multiply components and then add them.
Mm-hmm.
We could like call that something. I don't know. Let's call it a product for now. We just took the product of U and V. Let's scroll down here.
Product.
So, and I'm going to use here perpendicular vectors, two vectors, A and B, A1, A2, B1, B2. This is subscript notation. Are perpendicular if A, then there's just like this multiplication symbol. A, B is equal to 0, where A, B is A1, B1 plus A2, B2.
So you're just like defining a new way of multiplying things.
Yeah. Multiplying two things that based on our previous definition of multiplying couldn't be multiplied. You know what I mean?
Mm-hmm.
Because like multiplying two numbers, that's like taking the second thing the first amount of times, like 2 times 5 is 5, 5, 5, 2 5s or whatever, or 5 2s. But
Mm-hmm.
vectors, they have direction and magnitude. So it's kind of weird. You have to take the direction into account somehow. But for now, let's just define one way to multiply vectors as the multiplying the two first components and adding it to the multiplying the second two components. That was a really hard sentence for me to say.
Okay.
But it's right there. All right, so with that said, we have a little rule for perpendicular vectors, and we have, of course, the A equals KB for parallel. Got 3 examples here. Are they parallel? Are they perpendicular? Or are they neither?
So for one, it looks like those are parallel.
Parallel?
And the reason I'm thinking they're parallel is because I'm actually not trying to scale one up to another. I'm factoring out. So I know that like A is going to be 4 times 1 comma, oh no, not 4. 2 times 1 comma 4 with that scalar. And then I know that B is going to be negative 5 times 1, 4. And so from that, there you go. We got some scalar times a vector that's the same.
So basically 2, 8, negative 5, negative 20, and 1, 4 are all parallel to each other. I wonder if 1, 4 would have a name. I don't know.
Like just
Anyways,
naming that vector.
Parallel. So we have unit vectors. We have, I wonder if 1, 4 being, I don't know. Maybe if we made 1, 4 a unit vector, it could be like the basis for one dimension. I don't know where my brain's going. All right, we got so that was parallel.
Parallel.
7, 4, and 9, negative 12. The second one has a negative, and the first one doesn't, so I know they're not parallel.
you know they're not parallel.
Well, that's not true. Let me take it back. In one, the second one has negatives and the first one has positives, but they are parallel.
Right.
The second one, there's just clear misdirection. It's a magic trick. We could do a magic theme sometime. Anyways, so we need to check for perpendicularness.
Okay.
7 times 9 is
63.
63. And 4 times negative 12 is 48.
Yeah.
There's some that product is not 0. And they're not parallel. Therefore, neither.
Neither.
Let me scroll down. We got one last one, and we are seeing the vectors written differently, but still a valid way. Just think about it in your head. We have 3 1 zeros being summed with 9 0 1s. 3 9. Negative 6 1 zeros and 2 0 1s. Negative 6 2. Let's see. We've got negative 18 and positive 18.
Yep. That's nice. Oh.
Are you writing it?
Wow.
One of these days, we're both going to write it, and it's going to be perfectly inlaid. It's going to be really nice.
I don't know. I think my 8s are less consistent than yours. Because you've practiced doing your infinities. So then by virtue of that, I'm sure that your 8s have gotten better as well. Perpendicular.
All right. There you go. There's basics on vectors. Hopefully the video didn't get too long. But just to recap real quick, vectors are things that have both magnitude and direction. For these geometric ones, we ignored the magnitude because we didn't have a measuring tool. Curse you, Kami. But we did add and subtract vectors by the head to tail method. Then we started to realize that algebra and just notating it with these brackets, these corner brackets, is an efficient way to do vector math. So corner brackets, adding and subtracting, you're just adding coordinate-wise, x's with x's, y's with y's. You crabbed me here. We talked about unit vectors. This is just a long basics lesson, parallel and perpendicular vectors. And here we are on the other end. Any words of wisdom? Yeah. It's kind of like, well, you know, never mind. I was going to complain about my least favorite song from the movie Moana, but
oh, we've talked about that already, though.
Oh, we have?
Mm-hmm.
It came up in conversation with someone recently. All right, there you have it. Vectors. Geometric and algebraic vectors. We'll be doing mostly algebraic vectors from here on out. I have some words of wisdom that I thought about ahead of time.
Cool.
Can I share it?
Sure. Well, I think of something.
Yeah. So we've been doing these past few lessons. And for, I don't know why, but you just keep coming at me with these really cool perspectives that I never thought of before. And it made me think, do math with others. And it made me happy. I was like, I'm really happy that I'm doing these math lessons not by myself, because I have learned a lot, specifically in these past few lessons. Not that I didn't previously, but these last few, you just keep coming at me with new ways of thinking.
Cool.
Yeah. That's my words of wisdom. Do math with others.
Mine is similar, but not the same. It's always be teachable.
Always be teachable. No, I think that is very similar. Always be teachable. What makes you think of that?
I think it's really important to have like a sense of like, even though you may know some things, there's always things that other people know or ways that other people look at things that is valuable and worth listening to with the whole of your brain, not just like half your brain just like smiling and nodding. But
that's kind of what I'm doing right now. I promise I'm listening with my whole brain.
Cool, thanks.
I like that.
Not your whole brain though. Like you need part of it to be like breathing and stuff, but like with the whole of your attention. Mm-hmm. And it's a really helpful way to go about doing things, especially as you go further in learning things that, it just gets, I think it's hard to stay in that mindset as you learn more, but bringing yourself back into that mode is good. It's helpful.
Yeah. I can't tell you how much I learned. I went to college, I got a degree in math, and then I came back to high school to teach. And I'm like, there's still so much I don't know. And I think I've learned more these past several years being a teacher than I did like even in college.
Yeah, because you have to like justify it to other people.
Yeah. Yeah. There you go. Be teachable and do math with others.
Yeah.
Awesome. Let's close this one out.
Hats off.